All right, folks, we've come to one of my favorite subjects in Chapter 3. We're actually bouncing back to Chapter 3 for a little bit to study composition of functions, and then we're going to get into inverse functions. Functions can be combined in a number of different ways. Like you can add functions together, you can take two functions and multiply them together, or divide one function by another function. But one of the most important ways to combine two functions together is using an operation called composition. So what is composition? Well, let's say you take a number, x, and you put it into a function. Let's call that function g. All right, then what's going to come out the other side as your output would be g of x. The idea of composition is you take the output and say, let's take that and put that into another function. So let's call that function f. Then what's going to come out the other side would be f of whatever the input was, okay? And the input was g of x, so this is f of g of x. We've already talked about evaluating a function, and we've said that, whatever you stick into the function is, what comes out the other side is f with that thing stuck in. And we've been, we were like evaluating functions at things like x plus h, or your 2x plus 5 or whatever, and that technically we were doing composition of functions back then as well. So the idea here is we're putting one function inside of another function. Let's say, for example, that this function g of x is defined as giving me x squared. Okay, and then let's say that this function f it takes in an x and it gives me x plus 5. Well, it's a little bit confusing because if x is what you're referring is if x is the variable that is your input to the g function, and you're taking the g of x and sticking that into the f function, then to talk about f as having an input called x is a little bit confusing because technically when in this composition, we're never actually putting x into f. That doesn't happen here, right? X goes in g, and then g of x goes in f. So what you'll sometimes see, and what I like to do, is to write the function f out in terms of a different variable. And the common variable that is used is the letter u. U is often introduced as like an intermediate variable that plays a role in between. So this output from the g function can be called u, and that u becomes not only the output of g, but also the input of f. So I'd write f of u equals u plus 5, like that. Okay, so this, I think I've talked about u substitution before when you are trying to solve a complicated equation, which might be in like a quadratic format, but then there's something replacing the x. We have replaced that with u and then solved for u and then backtracked and solved for x. That u substitution concept, which is useful for solving equations, is also exactly the same thing we're talking about here with composition, just so you know. So what we have now is x goes into x squared, and then that output goes into u plus 5, and then something would come out the other end. Let's do this with a specific value. Let's take 2. 2 is going to go into the g function, and I'm going to go ahead and write g of x equals x squared right here. So when 2 goes into the g function, what comes out should be 2 squared, right? So this is going to be 4. So 4, we're now going to consider that to be the value of u, and that is going to be going into our f function. And f of u is u plus 5. So if 4 is our u value going into this, then it's going to be 4 plus 5, so 9 comes out the other side. And we can say that f of g of 2 was equal to 9, okay? Now what we want to do, the idea of composition of functions is this. It's like putting an input through a sequence of functions instead of just one. But what we want to do is now combine these two functions together into one function. And that one function is going to be called f composed with g. And it's notated f circle g, like that. So x is going to go into this one big function, which essentially can be thought of as take the G machine and the F machine and just glue them together so that outputs from G go directly into F without ever coming out. You never even see what's going on inside here. Things just go straight through. And F circle G is what you call that function. So what comes out the other side can be called F circle G, in parentheses, of x. So F circle G is the name. You should actually say this F composed with G of x, but that can also be written as F of G of x, like that. That's a G. Okay, so with these examples that we had back here, with this G of x and this F of U, that I was defining here, if we want to evaluate that and figure out a rule for F composed with G, F composed with G of x would equal F of G of x, and then you could take the G of x and replace it by its rule of assignment. So this would be F of x squared. I just took G of x and replaced it by x squared, because G of x equals x squared. Now I can apply the F function. This x squared should be considered like my U input. So U is x squared. So if F of U is U plus 5, F of x squared is going to be x squared plus 5. And there we go. That is the rule of assignment for the F composed with G function. Okay, this is basically the result of composing these two functions together to create a new function. So that is the basic idea and sort of the theory behind composition of functions.